So, welcome to Collaborate number two. Hope everybody's having a great week. Hope for everybody's based in the US right now. You all had a great Labor Day. Um, I had a chaotic Labor Day. Wound up in the ER with my 7-year-old. So, if you emailed me yesterday, it was a little bit late on the response. So, I apologize for that, or it was from my phone. So, it's there. So first things first, before we get going into module two, let's close up module one because your homework's not officially due yet. Not due tomorrow. Labor Day is one of the reasons your homeworks aren't due until Wednesdays right now. Because we came back off a holiday. I wanted to give you an extra day. I wanted to have conversations and do stuff like that. So before we jump into that, any questions from anybody? I've been getting a lot of emails, and that is fully expected. Like, that is the one thing I want you to do. And I was explaining to Christina a second ago. If you're confused, if that's the type of thing, one of the things I want you all to get used to being able to do is ask questions. One of the things I'm a big believer in, if you're working in analytics or data science or AI or whatever we're calling this field this week, because it evolves regularly, you have to get used to asking questions and talking through problems. So if somebody's confusing in what they're asking, if they're doing that type of stuff, you got to be able to bounce the idea, or you got to be able to talk through, what did you mean by this? Can you clarify those type of things? Never be scared to ask me a question. Never be to say, hey, this confused me a little bit. Can you clarify? That's the thing.
It's Michelle, Mick. I have a quick question about the markdown notes for module one. I'm going through those pretty closely to help me with code for the homework questions.
Yeah.
One of the examples, so I'm just thinking through the logic for the college apps that come from public versus private. I do see the code for the example about the SAT scores that you had in mod one.
Yep.
Wondering if that logic is similar, or am I on the wrong logic? Because there were a couple examples. There was the SAT scores, and then there was
So there's like three examples you could use for that one, right?
Really? Okay.
Yeah.
Okay.
There's a lot of ways to do that one right. Okay.
Yeah. Then let me just narrow down and ask about a function that I see here in the SAT score example. You're using a function that looks like rep with the the argument. Is that the actual function to do the randomized sample?
No,
No.
sample will do that for you. So the closest example you're going to have in anything I've given you from a notes for that one is going to be off the Collaborate.
Okay, I will go in there. Yep.
Yeah.
Because I thought, REP does not look like the function that I need.
No,
Okay.
that's REP is
Is replicate.
yeah. Another one that's really close is the it's the AI versus ML, or not AI, the human versus ML one. That we about the marketing strategy.
Okay. Okay. Thanks. I'll just, look at the yeah. Good. Thanks.
Not a problem. Any other questions, Joe?
Brad, for the worst part of just sounding like the biggest idiot in the world, I'm getting absolutely destroyed on the math notation stuff. Do you have any sort of place where I can possibly go and try and catch up there?
So on the math notation stuff, that would be it depends on what notation you're trying to catch up on, right? If it's in the module one stuff, that's going to be in the stat review, right? And if it's in module two, I will tell you, don't get killed on the math notation. There's some stuff to pick up on that we'll talk about tonight. But like the derivations and that type of stuff that's in module two, my best advice tonight that you're going to hear me say over and over again, focus on the code, focus on the application, and you're going to see tonight what we're going to focus on the rest of the class, which is mixing the model interpretation with the code. and how we pull that out and what we're taking away from it. Okay. That's going to be the biggest takeaway because everything else after that is really getting into the deep, deep stuff. And some of these notes are written for you for 3 or 4 years from now when you're deeper into this stuff. Okay. So what I do is I use my notes, and this is a reminder because I say it, and I know I shoot a ton of videos for you, right? Because I think videos help supplement reading, and you have all heard me say this. I try and teach a class I'd want to take, which that's the best thing I know how to do, right? Like I try and do that. My biggest thing is I wouldn't want to sit and read and read and read, right? So I try and shoot videos that you can interact with and play with. Um, I would struggle to read through everything. So I try and shoot videos that highlight the important stuff. The notation can get daunting, and I agree with that. From that, when we talk about muse, when we talk about means, I try and use the real language of what these things are. When we get into those things, the thing I would tell you is if we put a hat on it, or if we put anything over the top of it, it's an estimate, which means we're plugging in a number someplace. So that's what's going to be pulling out a code for us. But the code part is what matters, right? Like from a functional, personal standpoint, the code is what matters. And then where we're getting ready to go in module 2 from a standpoint of what you need to be able to take away, if you can work through the code tonight and the collaborate tonight, you're really, really taking away what you need to take away. If you can do the homeworks and you can fight through the homeworks, you're really getting what you need out of it. And that's the big thing I would tell you. Does that help, Sean?
Yeah, brother. Thank you.
Not a problem. Like y'all, the method to my madness, and I will tell you this because I just sent you an announcement. Been trying to send it all day, and people keep pulling me into meetings. Like my days are fun right now. Been trying to send y'all an email since this morning. I'm dead serious when I say y'all are doing great. You're interacting with the material the exact way you're supposed to be. This is new for many of you. Coding is new. That's part of the reason I asked to teach this class up front. Okay. I want to be the one to help introduce it to you. For better or for worse. And some of you are probably like, Brad, you suck at this. And that's fine too. You're allowed to tell me I'm bad at stuff. But it's also one of these things where I want to help you fight for it. Okay. I want to help you work through it. The key to success in this class is just working hard at it. Okay. I will promise you that. I will promise if you show up, and by showing up in an online class, I mean you put in the time and the effort and you do the assignments, you'll be fine in my class. I promise you that. That goes a long way in this class. I've done this for a few years now. The gray hairs are giving me away, like I said. But it's one of these things you will be fine in this class. You will have success in this class because we've designed this class to help you learn this stuff. Okay. So without me rambling a ton tonight, because I do want to stay on this, try and stay on the 6 o'clock side of 7:15. Let's get into some of this if nobody else has any questions on homework 1. I did post group discussion 2. I made it live. You all keep me honest because this new Blackboard, I think everything's visible to you all and it's not visible. I know at some point I'm going to miss the group discussion being visible, and I've already got my plan for when that happens, okay? Because the group discussion, I already know what that group discussion is going to be. And y'all are, it's like I said, when I make mistakes, it goes in your favor, right? So that'll be a good group discussion. It'll be there. And remember, the group discussion is just a small point of your grade. With that said, I've got Collaborate for tonight posted. I'm going to share my screen. This Collaborate's really interesting because we're talking about linear models, and linear models are probably my favorite topic. So I'm going to share my desktop, and we're going to talk about linear models. So if you go in and you go into your, let me make sure this has everything I need it to have. Yep. So if you go into, and let's make sure everybody can see my screen. Y'all can see my screen, yeah? Awesome. Let me get my chat up so y'all can make fun of me in the chat. All right. So now, so you go in, you see module 2, you can come down here. I have a couple things posted for you. And you all, if you all saw the announcement, you'll see what I have posted for you. I've got the Collaborate week 2 file, and I've got the extra example that's from Orange Juice. This is about a 20-minute example where we go through some extra content. talking about interpretation. I'm talking about how to fit models. I'm talking about why we do some things. Okay. I'll shoot these every week from here on out. Every week, you'll have about another 20 minutes of examples. And I know you're all rolling your eyes and being like, Brad, really more videos. Don't have to watch them. But it's one of these things where this is just an extra applied example. Think about it in addition to collaborate, right? Click on the collaborate file for this week. It's going to run you into exactly this. You can download the file again right here. This is how you download the raw file. I'm going to take you through the R tonight. Okay. I'm going to take you through the R tonight because I want to go step by step through what this thing is. All right. Now, I want to talk through what this thing is, why we're doing it this way. Okay. And why we're doing it this way. I have the homework posted and I have the group discussion posted for this week. Since I asked you to use GitHub and we're using GitHub for the class, the group discussion for this week is on GitHub. It is what is GitHub? Why does GitHub matter? All of these things. So it's on GitHub. So your group discussion this week is something very, very relevant. I also do apologize about typos. You all figure out very quickly I can't spell. There's probably something going on with that, but it's something that we worry about later. And I do try and run spell check as much as possible. So it's there. So collaborate too for Buddha 525. I'm going to jump back and forth between the knit document and the RMD tonight so we can play with code at the same time. So you're going to see me move a little bit, stop me, ask me questions. Like I said, we're going to try and stay on the 6 o'clock side of 7:15. All right. So we learned a lot more code in module 1 than we're going to use in module 2. Module 1 is a lot heavier code than module 2. That's the reason I let you do it in groups, is because I'm asking you to learn to code really, really fast. I give you 2 weeks to do it to turn into homework. And then I put you in module 2 and say, really, this is what the process looks like. Module 2 is about regression. Regression, you'll hear me say it a bunch, is the study of dependence. Dependence is about relationships. It's about how two variables relate to each other. And we get really complicated in it. When I say complicated, think cool. We learn to talk about associations really, really fast. And this is where I think higher order statistics and higher order machine learning starts. I'll be honest with you. I'm a PhD statistician who hated my intro stats class. I played college baseball, and when I played baseball, I took my first intro stats class that spring. I missed a ton of my stats classes because of that. And I thought it was the most boring class in the world because intro stats is not how you actually do statistics. Statistics doesn't start until this level. When we're building predictive models is actually what advanced statistics and what we do for a living, this is what it's about. It's about analyzing data and looking at relationships and taking complexity into account and starting to think about what predictive models are. It's analyzing complexity and thinking about building predictive models. When we start doing that, that's where real statistics kicks in. This is what got me into the field. So that's part of the reason I also like teaching this stuff, is because this is what it's really about. It's not about, one sample t-tests and one sample confidence intervals. That's where we can teach computing. So the thing I'll tell you, if we're going to learn 4 functions tonight, the first one we're going to learn is LM, which stands for linear model. The second one, we're going to learn to take a summary of LM. The third one, we're going to learn to create scatter plots. And the fourth one, we're going to talk about added variable plots a little bit. Focus on these for the module, and you'll be good. You'll be good. Now, regression looks really complicated on paper. Everybody makes it way more complicated than it needs to be. But in reality, all we're trying to do is depict trends and relationships with equations. A very famous statistician, and the truth is you can't really be famous as a statistician. There's no such thing, but we'll say you can be. They once said all models are wrong, but some models are useful. All right? And this is something that got really highlighted in the past few years. All models are an approximation of what we think is happening in the real world. We're trying to lay some sort of mathematical function out there to say this is an approximation of what we think is happening in the real world. Can we predict something off of it? Can we talk about what's happening? In most cases, this is very true. What we're trying to do is put a line through data. or in the real world, we're trying to put a hyperplane through data. And what we talk about with a line and a hyperplane, it's a line. So in 2 dimensions, the edge of my paper is a line. In 3 dimensions, it's a hyperplane. So it's like the edge of the paper up here. That's the best thing I can tell you the difference between a line and a hyperplane, right? So I can tilt it in 3 dimensions. Do you know how to make that look in 4 dimensions? You win, I'll come work for you. Okay? That's how this works. Now, the idea is they're not exactly right. But what happens is they can provide insight. The thing I need you to understand is, why do we start with regression? It's because regression is the method that most higher order models depend on. Whether we're talking about neural nets, which you all in the Buddha program will get to very, very soon after my class. Regression is a neural net. All right? Regression is a neural net. It's how we teach everything. All right? So what we're trying to do is something like this. We're trying to say the expected value of y given x is equal to beta naught plus beta 1x. Now, this is an equation you've seen your entire life. Whether you realize it or not, you've seen this since algebra someplace. Except all I'm saying is the expected value of y given x. I want you to say this is just the average value of y when you know x. This is the average value of y when you know x is equal to a y-intercept plus a slope times x. Beta 1 is just a slope. X is a variable. Beta naught, that's what we call this thing, is an intercept. It's your y-intercept. You've seen this written as y equals mx plus b. All right? You've seen that written before. You've seen the equation of a line. That's all this is. All we're saying is we want to say the average value of y at x is equal to this line. Because we have data and we believe in variation because we believe in statistics. Now, what we need to do is, because data has variation, is we need to estimate these things. These are parameters. This is a population intercept. This is a population slope. So we need to estimate them. To do that, we minimize what's called the residual sum of squares, which is we're trying to minimize the variance around the line. We're trying to minimize the variance of our data around a line. That's all we're trying to do. Find the best line that minimizes the variance around the line. That's all this does. So we come up with this equation, all right, where we put hats on this equation because we've now estimated. The estimated mean of y given x is equal to this estimated intercept plus this estimated slope times x. All right? It's just the predicted average of y given x at these points. Now, all we're doing is plugging in these estimates. Now, rather than talking about it, let's use the data you used for homework 1. So I'm going to go in here and we're going to talk about this. So let's talk through this. We're going to use college data set. You guys are familiar enough with this at this point. All right. Now, let's look at the relationship between enrollment and apps. Does that look like it follows a straight line?
No.
Why doesn't it?
Somewhat through the middle. Somewhat, you know.
Can I put a line
Roughly,
through
I
that?
guess. Yep.
Does that point bother anybody?
I didn't even, if we can drop it, we don't care.
Well, I'm sure Rutgers has a huge problem with it. Like, I don't mind losing Rutgers personally. I'm kidding. Rutgers is a great school. My mother and father-in-law went there. It's the greatest. But it's also one of those things where we can't just drop data. We'll talk about that in a moment. Okay?
No, I know.
But to me, that looks like a limit, right?
Yes.
Minus that data. What else y'all see?
Highly concentrated down at the lower bodies. And then you have more variance when you get further away.
It shows that like more applications, the more higher enrollment, generally speaking.
All right, so we got higher applications, higher enrollment, which makes sense, right? We got, there seems to be a trend. Look at what happens here, though. Now, this is something I want to catch your eye on right off the bat. And this is something I want you to see going on. Do y'all see like a cone starting to form? I'll call it a cone.
Yes,
Megaphone.
absolutely. Yep.
Gator mouth. However we want to talk about it. That's what we start calling non-constant. Okay? I want you to keep an eye on that. When we see that, let alarm bells. Okay? Now, watch what happens when I do this. Is that a straight line?
No, that's like curving. I mean, it looks like it's sloping upward, it's more curved.
So I
It's an
took
exponential function.
Yep. I took log of this college app. Michelle, I'm gonna put you on because I'm catching some feedback. Okay?
Sorry about that.
No, you're good. So see what it did to the data point right here, and I'm pretty sure this is Rutgers, right? It took the number of applications and the number of enrollment, right? And it pulled, when we took the log, it pulled it back in. So it took something, which we consider this a leverage point, and I'll show you the difference here. This is something that makes alarm bells go off in our head. You all are used to calling things outliers, right? One of the things I want to get used to calling, and you'll see this in the module, outliers in the X space. So something that has an extreme predictor value is called a leverage point. Okay? A leverage point. So this is extreme in the X space, but not necessarily the Y space. It's extreme in the X space. All right? It can be called a leverage point, right? So if I take the log of it, watch what happens. Go to the next spot. It pulls it in. Now, watch what happens if I take the log of both for a second. Is that a straight line?
Yeah.
Closer than the rest.
Would we call it good enough?
I mean, I would,
Maybe.
but I'm done.
Hey, listen. We'll play optometrist for a second. A, B, or C? If you had to pick one of the three, which one are you taking?
3.
The
Taking the last one?
Yes.
What you
As
have,
a straight line?
if you have to put a straight line through it, are you taking the first one, the second one, or the third one?
One for sure.
I'm probably taking this one. This one has everything I like about it. I can put a straight line through it. This data point's not too far away. There's everything I can control about it. We'll talk about why here in a second. The idea being, visuals can help me right off the bat. Now, the way we did this, I just went through and started looking at data, right? This log thing right here, as you'll figure out listening to the orange juice example, is my friend. Because what it does is it starts making adjustments on data. It starts pulling data in. And this log transformation we have access to, what it's going to do is it's going to talk about percentage increases. All right? It'll say a percentage increase in applications leads to a percentage increase or decrease in enrollment, which is easy to talk about. And we'll talk about that as we go. Now, why did we go through all of this? Why did we go from here to here? Why did I take you through all of that? Because the idea is when I'm here, I have a whole lot of noise. I have a whole lot of instability. I have a whole lot of variability. As I move up from 0 to 30,000 applications or 20,000 applications, I start to see a lot of variance. See how that starts to spread out and jump around? And then I come out here and I've got somebody who just decided they're going to take every application known to humans, right? And we're only going to enroll 4,000 people. Because that's great. Love that. So what we have is we have this entire spread, right? Our job as somebody who's trying to model data and understand relationships is to decrease variability or control variability or try and model variability. When I'm trying to model it on this scale, I'm going to have some problems. So what do? I start looking at where can I control it. So the first thing I can get to is this log thing. And we'll talk about that process. But when we can visualize it this way and see that it gains some stability, we're able to leverage it, okay? Now, the model we're going to deal with is on this scale. It's on this log scale, all right? And we'll talk about why as we move forward. Now, we're going to fit a model that is on this log scale, okay? So as we move through it, here's what we're going to get. We're going to get log enrollment is equal to beta naught plus beta 1 times log applications. So log enrollment is a function of log applications. That's what we're trying to say. So what does it look like? So let's fit our model. All right. I'm going to fit my model. I'm going to plot it and I'm going to look at my line. To do that in R, here's what it looks like. Red line going through data. What do you think?
Looks like it fits pretty well.
Oh, looks like what we just said. As apps goes up, enrollment goes up. In this case, as log application goes up, log enrollment goes up. Okay? Now, I'm going to summarize what you're going to hear in the orange juice example. All right, I'm going to give you we're going to interpret it the normal way for a second, and then I'm going to give you a summary of what you're going to hear in the orange juice example. All right, so let's look at some output really quick so you can see what's going on. In our output, what you have is you have an intercept and you have a slope for applications. Okay? What we say is we have a y-intercept and then we have a slope for applications. The y-intercept is what happens when this variable is 0. So when log applications is 0. All right? The slope says when we increase log apps by 1, we expect to see a 0.8218 increase in the log enrollment on average. All right? We expect to see a 0.82 increase in log enrollment on average. Why am I saying on average? Because the response is the average of Y. Okay, it's the average of Y. Now, let me explain what this means. It says if I would go from 6 to 7, I would expect to see log enrollment go up 0.82. That is the slope of the line. These are just definitions of slope. It is rise over run. It says if I go from 6 to 7, I go up 1, which means the slope would go up 0.8, or Y would go up by the slope. So it's 0.82. That is just the algebraic definition of slope. You learned that back in algebra, okay? Not changing anybody's world here. We're just going back to taking what does the statistics definition mean. Now, what you'll learn when you watch the orange juice example is you'll say, when I have the log of a response and the log of a predictor, we can say it's a log-log interpretation. And what that means is I can step back and I can say a 1% change in the predictor leads to a slope percent change in the response. So this is the cool thing. I can say if college apps go up 1%, enrollment will go up 0.82%. So if apps go up 1%, I'll get a 0.82 bump in enrollment, or a 0.82% bump in enrollment. All right? So this is where I'm allowed to talk about growth. This is a real easy way. These log-log models are a real easy way to talk about growth. All right? But in general, no matter what variables I have, whether I have log, whether I have variables untransformed, if I increase the predictor by 1 unit or by 1, make it go from 6 to 7 or 7 to 8, make it change by 1, the response on average increases by the slope. Okay, that's the definition. All right. So if we plug everything in, here's what we get. We get log enrollment is equal to 0.6 or 0.0696 plus 0.8218 times log apps. Now, if we go through, how do we create that line? If we go through and make a prediction at every point, and we create a sequence of every point from down here at 4 clear up to 11, that's what that red line is. It is a prediction at every possible point. Create a sequence that is like 0.00001. That's what that red line's doing. It's creating a prediction at every point to construct that line. That's how you create it. But how do I create a prediction at any point? Well, what we do is we come down here and we say predict from this model using a new data point. So what I'm going to do next is I'm going to create a prediction at a school that has around 3,000 applications. So where would that be on this line? Well, 3,000 applications up here. Let's go look. 3,000 applications would be someplace down here. So it's where a majority of our data is. All right. So let's look at 3,000 applications. So if I want to predict around 3,000 applications, what I say is predict with my model. I say new data equals data.frame apps equal 3,000. Notice I don't give it log apps. I give it the number of applications. Okay. I have to give it a data frame to do the prediction. All right. So I say predict mod new data equals data.frame apps equal 3,000. Now I save it as pred 3,000 and I look at it. It comes back as 6.16. On the log scale, that's fine. But try and interpret that to somebody. Well, the number of log applications is 6.64. Great. I don't know what that means. So to get rid of that, all we do is raise it to the E power. So to the E power, we say EXP of pred 3,000. It says, based on our model, if you get 3,000 applications, you'll get 772 students enrolled. Now, why is this so important? It's because in higher education right now, one of the things a lot of people are thinking about is conversion. It's thinking about how many applications do I need to enroll? But this is also what we think about, and this is the higher ed version of this. This is also what we think about with customer conversions. If you're marketing, you need to think about how many customers do I need to touch to make X many sales? And then you think about what is my expected, revenue off a customer? I need 772 customers. What's my expected revenue? Multiply that times the number of customers. That's the revenue generation, right? That's what we think about in situations like this. That's how we approach things like this. So this isn't just Brad's using college data, right? This is how we think about modeling. This is how we think about how people come through that pipeline. This is one of the ways to model that convergence. Now there's others, but this is just one. Now, just a little bit of a reminder, e to the log of x just equals x. So that's all I did here. Now, let's get into the data just a little bit more. And this is probably one of the most important functions you have. Just a reminder, Mod was the model we fit, right? So when we fit this model, as a reminder, I said log enrollment tilde log apps data equals college. Now, what this is called the R formula language, where enrollment is my response and apps are my predictor, okay? Now, what this allows me to do is define my model. We looked at the output just like this, right? And this gave me a slope and a predictor. This gives me just the basics. When I look at the summary of my model, summary of mod, it gives me so much more information than I've ever had access to before. And this is the important part. I can test a whole bunch of stuff. I can look at R squareds. I can look at my model fit. I can look at everything I need to see. So what I have is I have my estimate for my intercept, my estimate for my slope, which we've seen before. But then what I have is I have two p-values here. This is my p-value. Does my intercept, that's testing the null hypothesis, that my intercept is equal to 0? Truth is, I don't care about this p-value ever. I don't care about this hypothesis test ever. I won't say ever, but rarely. In my 20 years of doing this, I've never cared. I'll just be honest with you. I've never cared about that test. I won't say never. I can't remember a time about ever caring about that test. Okay? I won't say I've never cared. I can't remember a time that I've ever cared about that test. I'll put it that way. I've never not looked at this test. This is the test that my eyes go to automatically. I have trained myself to look right there. I check here. I check here. I do not care about this. Okay? This is the test statistic. This divided by this is this number. This divided by this is this number. Okay? 0.82 divided by 0.01. Because what we're testing, does this slope coefficient equal 0? Why would we test if that slope coefficient equals 0? Let's come up here and look. If this slope coefficient, if that number is 0 at all times, plug a 0 in there. Plug a 0 in there. What does it tell me? Plug a 0 in there.
You would have B naught as that's all that would be remaining.
So it says what? X doesn't matter, right?
Yeah.
And if X doesn't matter, what are we doing all this for? Just shut it down right now, right? So if X doesn't matter, what are we doing all this for? So the idea that we're setting this up and doing it this way, this is the most important test we have. This is the most important test we have. Is this 0 or not? The null hypothesis is the slope is equal to 0. The alternative is the slope is not equal to 0. All right? Now, you come down here, you look. If the p-value is small, meaning less than whatever threshold you set, 0.05 is fine, right? You reject the null hypothesis. The slope is not equal to 0. So if I'm looking at this p-value right now, that says it's less than 2 times 10 to the negative 16, which means it is basically 0. I reject the null hypothesis. The slope coefficient is not equal to 0. You're just looking for that number to be small. Okay? It has these stars, and here's the significance code. If it's triple, like if it's these three things, it's between 0.01 and 0. If it's 2 stars, it's between these numbers. If it's 1 star, it's between these numbers. If it's a dot, it's between these numbers. If it's nothing, it's between 1 and 0.1 or 0.1. Okay. The other thing you have access to, you have this thing called R squared. When you're in simple linear regression, which means you have one slope coefficient, because we're going to talk about multiple linear regression here in a minute. When you have one slope coefficient, what it's telling you is this is the correlation squared Okay, it's two things actually. It's the correlation squared between the response and the predictor. Okay. The other thing it's the percentage of variance you've explained by using the response. So 100% of the variance, 100% of the variance. I want you to think of the variance of y, up and down, vertical variation. All right. Up and down, up and down, up and down. And I see a couple questions in the chat. I'll get to them here in a second. Up and down, the vertical variation, right? Up and down, vertical variation, right? This is 100% of the variance. What we have left over is the variance around the line, how spread out we are around the line. So the difference between the total variance, the spread when we don't know x, so how spread out is it up and down this axis versus how much is left here. In our case, we were able to explain 85%, or right around 85%, which is a whole lot. We got 85% of the variation. Okay. All right. Couple things in the chat here before we move on to this next thing. So, Ethan, taking the log of both variables always result in the best data spread. No, we don't always just get to take the log of both variables. It's a nice trick that works sometimes. It's the thing I always check, but we'll get to a lot of that in module 3. Sean, so even though we're really close, we're not close enough to say the null is correct. So we never say the null is correct. The phrasing is we either reject the null or fail to reject the null. Basically what we're saying when we say we reject the null, in this case, this is a really, really small number. We're saying we reject the null hypothesis. The slope coefficient is not equal to 0, right? We're saying we have enough information to reject the null hypothesis because we're saying this doesn't come from the distribution where the slope coefficient is equal to 0, right? That's kind of where we're at. And then what we're able to say in like this case. So let's just look at this here. Let's just look at what happens in this case. So we're testing the hypothesis that the intercept's equal to 0. All right. We fail to reject the null hypothesis, right? The slope coefficient could easily be equal to 0. We can't tell that the slope's not, or the intercept's not equal to 0. So remember, to the clarification there, the null always has the equal sign. The null always has the equal sign. The null hypothesis always has the equal sign. So the null hypothesis is the slope is equal to 0. In this case, the null hypothesis is the intercept is equal to 0 in this case. The null hypothesis always has an equal. Good questions. All right. Any other questions before we move on? Y'all good? All right. So let's add a second predictor this time. All right. So remember this number. Remember the 0.82 for a second. Okay. Remember the 0.82. Keep that 0.82 locked in your head for a second. I'm going to fit a model that takes out-of-state tuition because we know cost has to come into a play with enrollment. Like it can't just be the number of applications. The number of applications has to dictate enrollment because you can't have more kids enrolled than you have number of applications. But just like anything else, like customer conversion has to come into cost as well, right? So how do we add another predictor? Well, in R, it's really simple. I'm just going to add the predictor. So let's do that. So what I'm going to do is I'm going to come in here and I'm going to say log enroll tilde log apps plus out of state. So let's run it. Then I'm going to look at my model. Well, my intercept is 0.4. This is now 0.84. What was it before? It was, let's come up here. It was 0.82. So see how the coefficient changed? And now out-of-state tuition is a really small number. So it's -4 times 10 to the negative 5. You see this e to the negative 0.5? What it says is that's times 10 to the negative 5. So it's a really, really small number. So now let's look at the summary just to see what we're getting ourselves into here. So we said the intercept doesn't matter as far as the test, but let's look at these two coefficients. What these two coefficients are now, and then we'll interpret the coefficients, right? We'll interpret the coefficients, and I specifically want to look at this one. It says, test the hypothesis that log app's coefficient, slope coefficient, is equal to 0, given everything else is in the model. So in this case, out of state is in the model. Why do we have to consider out of state in the model? Well, look at this. See how it's 0.84? What was it before? 0.82. Why do you think the coefficient changed? Because behind the scenes, and as you go through the module this week, what you'll find out is these models are smart. These models know what unique information each one of these variables provides. And by bringing that unique information into play, it's able to update the information it brings into the prediction. All right? So what it's saying is, based on the fact out of state is in my model, my new coefficient estimate, my new slope coefficient estimate for log apps is 0.84. All right? So the next question is that significant? Based on this p-value, the p-value is less than 2 times 10 to the negative 16, which is almost 0, which at any level of significance is significant, right? So it's less than 0.05. So we reject the null hypothesis. The slope coefficient for log apps is not equal to 0, which means there is a relationship between log apps and log enrollment given out of states in the model. All right, let's go down here to the next one. Look at it. Check my p-value. My p-value is really, really small. My conclusion, all right, this is significant. So what am I able to say? I reject the null hypothesis. The slope coefficient is not equal to 0. So there is a relationship between out-of-state tuition and log enrollment, given log apps is in the model. Okay, that makes sense. Both of these things make sense. It says, even when I take into account the number of applications in the model, out-of-state tuition still is going to affect enrollment. That makes sense. And given when I take out-of-state tuition into the model, the number of applications I get will still affect enrollment. I can't have more people enrolled than I see as a possible customer, right? So these are the things that we're looking at. These are the things we're thinking about. So what does it actually mean? Well, we talked about how to interpret log apps last time, so I'm not going to push that one again. But let's talk about this out of state for a second. How do we interpret this? Well, out of state tuition is in dollars. So it says for every dollar increase, we expect the average log enrollment to decrease. Decrease. Why decrease? There is a negative sign here. By 4.6 times 10 to the negative 5 on average. Because here's the thing. Why does that make sense? Because tuition never increases by $1. Tuition increases by $100. Tuition increases by $500. But it's there. So when we're interpreting this here, we can say that's the interpretation of the coefficient. When I would interpret this for a client, or when I would interpret this for a school, I would do it on the scale they would move tuition, right? I would look at their next average tuition increase or their previous average tuition increase, right? I would say this is by $50, or this is by you increased tuition last time on average $100. So I would multiply this by 100 and say we would expect enrollment to decrease by this on log scale. And then move it that way, okay? That's how we talk about this move. All right. All right. That's how we look here. So there's a question in the chat. How do we know when to add log and when not to? In the original example, when we started this problem, I was showing you how to look at graphs and how to do this one. I just added out of state in this context to show you an example of how to do that interpretation. When we get to module 3, I'll show you the full scale of how we do the logs and those type of things. Right now, I just wanted to show you how to do one-off interpretations to focus on that statement. When you get module 3, you'll know how to do all of that piece, okay? I just wanted to show you how to do the one-off of the interpretation itself, all right? Of this is how it looks without a log attached to it. When you get to module 3, and as you come out of module 3, you'll have all the tools to tell that difference. Does that make sense? Dylan, to your question. When we reject the null hypothesis, we are accepting the alternative. You don't want to use that language because somebody who's not me, who's a statistician, will like jump on it. And I'm the least formal statistician you'll probably ever be around. But conceptually, yeah. When you reject the null, you're basically saying, I'm confirming the alternative, right? I'm saying I'm moving to the alternative and accepting the alternative. That's what you're coming to. Yeah. Like without having to go to the math PhD level stuff, yeah. But just say we reject the null. That's the way you want to go that direction. But in your head, you can be like, yeah, I'm coming to the alternative piece that I'm moving this direction. Anything else on this? Are you all good with this interpretation piece? We will interpret almost every model we look at in some way. I won't do every coefficient all the time, but we'll interpret at least one coefficient. The other piece I want you to see here is this R squared. The R squared here is still the percent of variation explained by the model. It basically says I can explain almost 90% of the variation, so 89.3% of the variance of the response just using these two variables, which is really cool. It says I start off not knowing what's going on with enrollment, and just using these two things, I can explain almost 90% of the variance, which is the whole goal of regression. It's trying to explain what's going on using these predictors. Can I get to what's going on? So it's a really, really cool idea. All right. Now, added variable plots really are about trying to give us unique information. So getting to your point of why I would ever use out of state when I have access to this information. It's about unique information. Why would I create a more complex model when I don't need to? Added variable plots at their core allow us to do something, and it's visualize what information models are bringing to the table. And I spend some time on this in the module, so I want to take a second and walk you through it. So the idea is if I'm looking to add out of state or out of state tuition to my model, given I know apps is already in there, what I'm trying to see is what unique information does it bring, given that apps is already in my model, okay? That's the entire goal. So what we want to look at is this, and you'll see how I get it. It's very simple. In library car, and this is a package I helped write, it's really, really widely used to the point where it gives me a headache. There's a function called AV plots, okay? And this is something where we use it a lot. What I'm going to show you, and I want to show you at this level because it looks a little prettier. Basically what we have here, and you'll see why I say given others. On the y-axis, we have log enrollment given others and log apps given others. What this means is these are the residuals of the model with log enrollment given all other variables but log apps. So this is log enrollment given out of state and log apps given out of state. What this is doing is looking at the unique information that's left in log enrollment given we know out of state, and given the unique information that log apps brings given we know out of state. Over here, this would be log enrollment given everything that's not out of state. So in our case, log apps, and out of state given everything that's not out of state that's in the model. So log apps. So what unique information does out of state have that log apps doesn't? What information are you bringing? I think of this as team building. If I'm looking to hire a team member, I need to know what are they bringing to my team that I don't already have. It's okay to have some of the same skill set, but if I'm looking to expand my team to something, I need some new skill sets, right? It's okay to have some skill sets that are same, but I need new skills, right? And if I'm looking to attack a new problem, I need to know what is left of that problem that I can't already get at. That's what this is. This is what's left over of the problem that I still need, given what I already have, versus what is this new thing bringing versus what I already have access to. And what this is the residuals, okay? This is the residuals of the model. All we did was fit a regression of out of state versus others, right? And what are the residuals? It's the leftovers. It's what I can't predict, right? So I'm looking at the residuals from this model, right? Looking at the residuals from the model of out of state versus log apps, and then looking at the residuals from log enrollment versus log apps. And then I just plot the trend. And what I see is there's a little bit of a trend. There's a little bit of a trend. And this is what I get from an added variable plot. So if you ever want to see if you need a predictor or if you need that feature, the added variable plot will tell you. This is just one of the ways to look at it, okay? All right. Any questions on added variable plots? This is something that really talks to you about why you build models in a way and why you build there. And we walk through it pretty detailed in the module.
Just a quick question for the code for the plots. I just
Yep.
wanted to go
Yep.
back up and thank you.
Right here.
Thanks.
So all you're going to do is fit a model. You fit the big model you want to fit. So in our case, we fit the model with both predictors in it, right? And so in our case, I fit a model with log apps and out of state, right? And then all we do is just run AV plots of that model. So it shows me what it added. Does that make sense? Awesome. All right. Anything else?
Yeah, I had a quick question.
Yep.
So is this relating to the 89% like prediction that you were referencing before the plots?
Yep. So basically, if I can get 85% with just using this, right? Log apps, we know that. The other 14% is now coming from when we use both pieces and this unique information, right? The
So
unique
sorry, go ahead. Sorry.
other 4%, not the other 14. I apologize. The other 4%.
So it's taking two variables and kind of seeing if there's a positive correlation, and then it's taking that to if it can predict it based off of a trend that it's noticing, and then that gives it its certainty that it's 89%.
No, so what it's doing is it's coming back and it's saying, look, how much variation that is there, right? How much of this variation am I able to explain? So what it's doing is it's optimizing it and then making that prediction, right? And then looking at how much leftover is there.
Okay,
So what
that
it's
makes
doing,
sense.
it's coming up with these estimates and then making that prediction and then seeing how much is left over.
So if its prediction is close to what is actually being forecasted, then that's what gives it a positive prediction, like saying it's closer to 100% because of how close it is to what is already being plotted.
Yep.
Okay.
In essence, yeah. Any other questions there? Going once, going twice. All right. As always on one of these, I like to give you a little homework help. Not that I like to give you answers to your homework or anything like that, but I like to give you a little homework help or a little bit of head start on your homework because some of the things I'm asking you to do in your homework are pushing you a little bit. And I like to do that, but I also like to give you a little head start and some code help because it's there, right? And you all are busy people and you work hard, and I want to help you there. So in your homework, I ask you to look at the transactions data. And I ask you to think about how you can create different models using the transactions data. And I ask you to look at averages and differences in the transactions data. And this is banking data that we've had access to in the car data set. So in the car data, what we're looking at is we're looking at times it takes to do two types of transactions at a bank. So here's the time, here's T1 and here's T2. And I ask you to really think about feature engineering, which is what we think about interpretation of models. So when you're plugging in stuff into a model, you think about what you actually want to interpret them as. We spent a lot of time talking about how we interpret coefficients today. Like, what's it mean to increase something 1 unit, right? What's it mean to increase a transaction T1 by one, right? It means you'd add a transaction. But if I would ask you to talk about the average transaction, increasing the average number of transactions is the same as increasing the sum of the transactions, right? If I increase the sum of the transactions, it's the same as increasing the average transactions, right? You're just adding. Increasing the difference in transactions means I increased T2 over T1. So if I want to do an average transactions, I'm going to create a new variable and I'll say transact $A equals transact T1 plus transact T2. Okay. So I'm going to construct that. That's how I'm going to do my averages. Now, if you want to do a true average, you could put a wrapper around this and divide by 2. That's fine. It's not going to change anything. But for all intents and purposes, if everything is two things, the sum is the same as the average. In this case, the difference is T2 minus T1. That's the way I did it. So the difference I'm going to save this way. Now, I can fit a bunch of different models. I ask you to look at a couple models. I ask you to look at a model with T1 plus T2, a model with the average and difference, and then M5 that have the average, difference, and T1 and T2, and talk to me about them. So what will be the interpretation differences that come up and see how these models run? The one thing I will show you, and we talk about something very similar in your notes, is these things right here. You shouldn't have models that have NAs in them. It means you're using redundant information. Think about why. Okay. This is a think about it problem. The code is really straightforward. Minus getting this set up, which part of the reason I helped you with it. Part of constructing models is thinking. That's one reason I talk to you about being problem solvers with data and technology. If you can get the code right, which Gen AI is a big help in some of this stuff now, it's thinking through why it's doing this stuff and why it's reacting this way. Gen AI ain't so good at that. Not yet, at least. It's not getting there anytime soon from what I'm seeing. But with this type of stuff, why would we want to interpret this way or this way? The other hint I'll give you is the predictions for both of these models will be the exact same. The interpretation at the coefficient level is different. Think about that and see what you come back with, okay? All right, y'all. Any other questions?
I had a question just about running like a piece of code. So when you're running like a confidence interval, and then so I guess you open it up and then you run it on your variables. So say in this instance, like boot is the variable you did, and then you open up the parentheses and you do like if you want to run an 80% confidence interval, it'd be like zero point 0.2 comma zero point 0.8, right?
An 80% confidence interval. So let's talk about that for a second. So an 80% confidence interval. What you're saying is that is an 80% confidence interval.
Yeah.
I would claim that is not an 80% confidence interval.
So it'd be like would it be the 0.1, 0.9?
I would claim this is a 60% confidence interval. I would claim this is an 80% confidence interval. Why? Because there's 0.8 between those quantiles, right?
Okay.
You see what I'm talking about?
Yeah,
0.1,
yeah, that makes sense.
0.9. The other one, there was 0.6 between them,
Right.
right?
Yeah.
So I'm getting an extra 20% moving each bound 10%.
Okay.
See what I'm saying?
Yep. Okay.
Yep.
I thought of it wrong before. That makes sense though.
No, you're good.
Thank you.
Anything else?
I had one thing. Can you go back up to the added variable plots?
Yep.
On the right hand one, it seems like the blue line should be a steeper decrease to best fit the data.
So what you're doing is you're seeing what you want it to be, right? You want it to come down through this, right? This data cloud right here is keeping that from happening. This goes back to the point where it may be better off to be transformed, right? And we'll get to that in module 3.
Okay.
Like I said, I threw this in here to show you how to interpret one, right? But we'll use tools like this and tools like others, or tools like this and some others that allow us to use plots like this to figure out if out of state needs transformed right here. But no, you're spot on. It might need a transformation because you want it to come down through here like this, right?
I mean, that would make logical sense, which isn't always accurate.
And remember, we're doing this on a residual scale too, right? So from doing it on a residual scale, it's a little bit harder to interpret what it should be doing and how it should be functioning.
Got it.
And we could be leaving another variable out that we need to be putting in, right? It could be an error of omission here because we're just using 2 and we need to use like 5 variables too.
Got you. All right. Thanks.
It's a great look. Anything else y'all need? From the standpoint of the theory that's in module 2, what I will tell you is don't get caught up in it. Okay? Don't get caught up in it. Some of that is for some of you who will be interested in it, who might be interested in it. Don't get caught up in the derivations. Don't get caught up in that stuff. Focus on the applied stuff. That's the only stuff I'm ever going to test you on. And when I say test you on, it's the stuff that's in the homework. That's the stuff you're going to use every day in doing this stuff, right? From the theory stuff, I have it in there because some people find it useful, some people who really push that stuff. But like I said, some of you will think about it and want it 3 or 4 years from now. Don't focus on it right now, especially if you're under time crunches at work with everything else going on in life. You'll have access to these videos and everything else for good. That's the reason I give you the notes and the videos. Okay. So don't feel like you've got to try and process all that stuff immediately. The other thing I will tell you, and the other thing I will ask you, and I will reinforce this, you're doing great. You all are doing online programs while you have life going on and everything else. You all are doing stuff not a lot of people challenge themselves to do. Understand how much I think of you for doing that and how much I support you for doing that. I'll do my best to help you. So just keep pushing yourself. And if there's anything I can do to help you, yell at me, okay? That said, that's all I got for you. Let me know if you need anything. Let me know how I can help. And yeah, just yell. Okay. Y'all have a great week. Okay.